So for day 13, we're going to talk about reviewing simplifying radicals. So for number 1, what we're going to look at is the square root and see if what's underneath is a perfect square. So if you look at number 1, is the square root of 36, which is 6. You don't have to break that up into 2 factors or anything since it is a perfect square. For number 2, be careful with the negative there. Notice the negative is on the outside of the square root, so it doesn't affect how we handle what's inside of the radical. So I'd put the negative still on the outside, and 100 is a perfect square, so I would just end up with negative 10 as my answer. For number 3, though, notice that the negative is underneath the radical, and what that means is I'm looking for a number that when I square it, I get negative 49, and that is not possible. A positive number squared is positive, and a negative number squared is also positive, so the way I'd write the answer here is no real number or no real answer. Either of those is fine, and that's just because you cannot take the square root of a negative number and get a real number. For number 4, though, we're looking at the square root of 50, and 50 is not a perfect square, so the way we handle problems like that is we look to split it up into 2 factors where one of them is a perfect square. So 50 has a couple different factor pairs. You could do 10 and 5, you could do 50 and 1, but the one pair that's going to be the most helpful is going to be square root of 25 times the square root of 2. Notice they're both still underneath the radical. And the reason why I picked 25 and 2 is because 25 is a perfect square. So then what I would do is deal with the square root of 25, which is 5, and then that square root of 2 stays square root of 2. So the answer is 5 root 2. For number 5, I'd handle it similarly. The only difference is I have that 5 that's being multiplied out front. So what I do is write 5 times, and then I'm going to split root 12 into 2 factor pairs. The one that I'm going to pick is 4 and 3, because 4 is a perfect square. So now I have 5 times the square root of 4 times the square root of 3. And then what I would do is take the square root of 4, which is 2. So I have 5 times 2 on the outside, and the square root of 3 stays the square root of 3 on the inside. So my final answer is 10 root 3. For number 6, I have negative 10 multiplied by the square root of 18. So I'm going to keep the negative 10 out there, and then I'm going to think about what I can split 18 into, where one of them is a perfect square. What I mean is 18 again has a few different factor pairs, but I'm looking to break it into 2 numbers where one of them is a perfect square. So the pair that I'm going to pick is 9 and 2. Notice they're both still underneath the radical because the square root of 9 times the square root of 2 is still the square root of 18. Sometimes we have a tendency to, once we break it up, we accidentally bring one of those numbers outside of the radical before we actually take a square root of it, so be careful there. So now I have the negative 10 on the outside still, and then the square root of 9 is 3, and the square root of 2 stays the square root of 2, so now I just multiply the numbers on the outside, and I get negative 30 square root of 2. For number 7, now we are going to multiply 2 radicals together. There's a couple different ways that you could handle this. You can either try and simplify each radical and then multiply them, or what I like to do is just multiply the 2 radicals together and then simplify. So what I mean is we have the square root of 20 times the square root of 5. So if I multiply those, I get the square root of 100, because 20 times 5 is 100, and that 100 should still be underneath a radical. And then I'm going to look to simplify the square root of 100. So first check is if it's a perfect square. 100 is a perfect square, so then the square root of 100 is just 10, and that would be your answer. Now if what I got wasn't a perfect square, then I would break it up the same way I did the previous few problems, looking to find a factor pair where one of the factors is a perfect square. So then number 8, the first thing I would do is multiply the 2 radicals together. So the square root of 2 times the square root of 8 is the square root of 16. And hopefully you notice at this point that 16 is a perfect square, so then the square root of 16 is 4, and that would be your answer. For number 9, slightly different problem. We're multiplying 2 root 6 times 3 root 3. Notice we have a number out front of each radical and then a number underneath each radical. So if I want to multiply them, you multiply the numbers on the outside together, which would be 6, and you multiply the numbers on the inside of the radical together, and 6 times 3 is 18. So what I have is 6 root 18, and then that looks a lot like number 5 and number 6 did, where we have a number on the outside and a radical to simplify. So I would look to break 18 into 2 numbers, where one of them is a perfect square. So I would break that into 9 and 2. Notice they're both still underneath the radical. And And then the square root of 9 is 3, so this becomes 6 times 3 times the square root of 2. So 6 times 3 on the outside is 18, so my final answer here is 18 root 2. So now the next few problems we are going to begin multiplying not just a radical times a radical, but sometimes a radical times a binomial, or a combination of a number out front and a radical times a binomial, and then we'll eventually get to multiplying two binomials together. But for now, root 5 times the quantity 7 plus root 2, first thing you would do is distribute that root 5. So I want to be clear there, there's really a 1 out front of that root 5. So if I multiply 1 root 5 times 7, what I should get is 7 root 5. Because 7 times 1 is 7, those are both on the outside. And then root 5 stays root 5 because there isn't a radical attached to that 7 on the inside of that quantity. And then I'm going to take 1 root 5 and distribute it to root 2. So root 5 times root 2 is 1, or just root 10. So that's the distributing part. And then here I want to check if I can add those together. In order for me to be able to add those together, those have to be the same radical. So I have one that's root 5 and one that's root 10, so they're not the same, and neither of them simplify, so that would be my final answer. So for number 11, I'm going to do the similar process, which is distribute that 3 root 3 on the outside times that quantity that's on the inside. So I'm going to show kind of the intermediate step that you may or may not need, but it's a good idea to get in the habit of doing, which is when I multiply 3 root 3 times 4 root 3, I would get 12 on the outside, 3 times 4, and I would get root 9 on the inside. And I'm going to leave it root 9 for now, and that's what I mean by that intermediate step. You may or may not be able to call that 12 times 3 right away, but you'll see how that works in a second. And then 3 root 3 times negative root 6. I have 3 times 1 on the outsides, which is 3. And then root 3 times root 6 on the inside, which is root 18. So 12 root 9 minus 3 root 18 is just the distributing part. And before I actually try and subtract them, I'm going to check to see if each radical simplifies. And like I said before, root 9 is really 3, so I can call that 12 times 3. And then I'm going to split 18 into root 9 and root 2, because 9 and 2 are a factor pair of 18, and 9 is a perfect square. So I get 12 times 3, which is 36, minus, and then that's 3 times, and that root 9 is 3, so that's 3 times 3 is 9, and then I still have a root 2. So what I have left is 36 minus 9 root 2. And those can't be combined because one has a radical and one doesn't, so that would be your final answer. For number 12, something very similar. I'm going to multiply, I'm going to distribute that. But first, what I noticed was that root 25 on the inside can actually be called 5. So I have 2 root 3, and I'm going to change that to a 5, because 25 is perfect square. And now I'm going to distribute. So if I take 2 root 3 and multiply it by 5, what I should get is 10 root 3, because 5 times 2 is 10, and I still have that radical 3, plus 2 root 3 times 2 root 3, which is 4 root 9. So 2 times 2 is 4, 3 times 3 is 9, still underneath the radical. And then I'm going to try and simplify each radical as much as possible. The only one that actually simplifies is the root 9, because square root of 3 doesn't have any perfect square factors, so it stays the square root of 3. So then square root of 9 is actually 3, so what that becomes is 4 times 3, which is 12. So my final answer there would be 10 root 3 plus 12. Okay, so then what you'll notice about 13, 14, and 15 is now we're not multiplying radicals, we're actually dividing radicals, or taking the square root of a fraction, which is a division. So the first thing I like to do for these is to actually split it into 2 radicals if it is a square root of a fraction. So I would call this the square root of 64 over the square root of 9. And then I would try and simplify each radical separately. What I notice is the square root of 64 is a perfect square, 64 is a perfect square, and 9 is a perfect square, so I could actually just call this 8 over 3, and that would be my answer. Because those are both perfect squares, they both simplify, now there's no radical. The one thing you want to be clear about when we're simplifying radicals and we have division is we don't want a radical in the denominator in our answer, and that's what we'll have to do for number 14. So the first thing I'm going to do is split it into 2 radicals, so the square root of 8 over the square root of 7, and then we have to do what we call rationalize this fraction. And what that means is I need to multiply the top and bottom of this fraction by something that would make it so there's no longer a radical in the denominator. So what that will be is if I multiply the top and bottom by the square root of 7, watch what happens in the bottom. So in the top I get the square root of 56, because 8 times 7 is 56, still underneath the radical. And then root 7 times root 7 is 7. And if you're not comfortable with that, here's why that is. I'm off to the side here. So root 7 times root 7 is really the square root of 49, and the square root of 49 is 7. So that's how that works. But if you're comfortable with just understanding that a square root of 7 times the square root of 7 will just give you 7, then that's really why we do that. So now I have the square root of 56 over 7, and the last thing I need to check is if the radical in the numerator can simplify it all. The bottom's already 7, there's no radical there, so we're okay there. But the square root of 56 actually does simplify, so I'm going to figure out how to break that up. And the pair that's going to make the most sense for 56 is 4 and 14, because 4 is a perfect square. So I have the square root of 4 times the square root of 14 over 7, and then the square root of 4 is 2. So my final answer would be 2 root 14 over 7. So kind of an involved process, but the whole idea there is we're looking to split it into two radicals and then rationalize so that we no longer have a radical in the denominator and that each radical is simplified as much as possible. Number 15, what you'll notice is don't need to split it because it's already split separately, the top and bottom, but there's only a radical in the denominator. So what I need to do is rationalize this, which would be multiply the top and bottom by whatever the radical is in the bottom, because what happens is the bottom will no longer have a radical in it. You'll see how that works here in a second. So what I get in the top is 4 root 5 over, and root 5 times root 5 is going to be 5, or the square root of 25, which is 5. And then the last check is, does the radical in the numerator simplify at all? No, it doesn't, so that would be my final answer. Like I mentioned before, the next sets of problems will be really focused on distributing, or in this case, double distributing. There's really two major ways to double distribute, which is multiply a binomial times a binomial. You might be more comfortable hearing it as FOIL. One of them is just draw the arrows and multiply everything in each quantity together. The other one would be to draw kind of a box as a reference for multiplying. So if I wanted to draw a box, it would have to be a 2 by 2 because each of those factors has 2 terms. And then I'm just going to put 1 on the top and 1 on the side there. So I'm going to put 4 plus root 3 along the top and 5 minus root 3 along the side there. And filling in every box would be the same as multiplying or foiling or distributing to simplify this. So in the first box I get 5 times 4, which is 20. In the second box I get 5 times positive root 3, which is positive 5 root 3. In the first box of the second row I should get negative 3 times 4, which is negative root 3 times 4, which is negative 4 root 3, and then negative root 3 times negative root 3 times positive root 3 is negative root 9. And at this point what I like to do is then take my 4 terms from inside the box and just list them in order. And the order isn't really that important, so that's my 4 terms from my distributing. And then I'm going to try and add or subtract anything that's like or simplify any radical that simplifies. So if you look, the middle terms, 5 root 3 and 4 root 3 are both root 3, so they can be subtracted. So what I have is 20, and then 5 minus 4 is just 1, so I'm going to write plus root 3 minus, and then the square root of 9 is 3. So I have 20 plus root 3 minus 3, and then the last thing I can do is 20 and negative 3 add to be 17. So my final answer should be 17 plus root 3. That would be the drawing a box as a way to organize it. It's not necessary, but it is really helpful so you keep track of your multiplying a little bit cleaner. So for 17, still have to multiply a binomial times a binomial. So if I draw a box there, real quick aside, if you don't need the box as a reference, you don't have to draw it. If you're comfortable distributing, then go ahead and do that. I just like to show the box for those of us who need another strategy to multiply this stuff out. So I'm going to put one of the binomials across the top and the other one along the side. It doesn't matter which one goes where because you're going to end up multiplying them all anyway. So I just fill in the boxes by multiplying the terms that bound the box or on the side. So 6 root 5 times 6 root 5 would be 36 root 25 because 6 times 6 and 5 times 5. And then the second box in the first row would be 6 root 5 times positive 2, which would be positive 12 root 5. And then negative 2 times 6 root 5 would be negative 12 root 5. and negative 2 times positive 2 would be negative 4. So that's the distributing there, or the double distributing technically. And then again, I'm going to list all 4 of my terms in order, just going top to bottom. And then I'm going to look to simplify, combine like terms, and then make sure all radicals are simplified. What I'll notice is the middle terms actually add to 0. 12 root 5 minus 12 root 5 is 0. And then 36 root 25, that root 25 is actually a perfect square, so I can call it 36 times 5 minus 4. And then 36 times 5 is 180. So 180 minus 4 is 176. So in this case, I had binomial times binomial, the middle terms completely dropped out, and then I had a perfect square as my radical, so my final answer just didn't happen to have any radicals in it, actually. Number 18, first thing we have to recognize with a binomial raised to the second power is it really means that it's that binomial times itself. So that's the first thing I would do. And then that problem turns into the same problem as the previous two in terms of how we'd handle it. So we have to multiply a binomial times a binomial. If I wanted to draw a box, I would. I'm going to show the distributing method in this case, or FOIL. 3 root 10 times 3 root 10 should be 9 root 100, and I'm going to leave it like that for now. And then I have to take that 3 root 10 and multiply it by positive 5, so I should get positive 15 root 10, because I multiply 3 and 5 on the outside. And then I'm going to take that plus 5 in the second term of the first binomial, and I'm going to distribute it to both terms of the second binomial. So I get 5 times 3 root 10, which is 15 root 10 again, and then 5 times 5 is 25. Those are the same 4 terms you'd get if you just drew a box. But this is just the other kind of way to handle it. Then I'm going to look for like terms and any radicals that simplify. So that root 100 is actually a 10, so that becomes 9 times 10. And then the two middle terms, 15 root 10 plus 15 root 10, actually add to 30 root 10. And then plus 25 I'm going to leave for now. So 9 times 10 is actually 90. And then the other two terms I don't touch yet. So then to finish this, I have 90 and 25 that add to 115. So my final answer would be 115 plus 30 root 10. So that is a binomial times itself, shown using a double distribute rather than drawing a box. But the box would work just fine there as well. Then number 19, I would do the first step the same as I did before, which is write that binomial times itself. And then I have to distribute that. Whether you want to draw a box or draw arrows, that's totally up to you. I'm going to draw the arrows rather than draw a box, just because I want to kind of show both methods a couple times. So root 6 times root 6 should be root 36. And then root 6 times negative 6 would be negative 6 root 6. Negative 6 times root 6 is negative 6 root 6. And then negative 6 times negative 6 should be positive 36. So then I'm going to look for any perfect squares or any radicals that simplify, and then any like terms. So that square root of 36 actually becomes a 6. And then the two middle terms are like terms. So I have negative 6 root 6 minus 6 root 6, which is negative 12 root 6. And then I should have plus 36. And then, looking for like terms, I have 6 plus 36, which should be 42 minus 12 root 6 would be my final answer. And then what you'll notice for the next problem, number 20, let me just back this up here a little bit, is I'm looking to add 3 terms together. The problem is, though, all 3 of those radicals are different, so I can't add them as is. I would need to first add any like radical terms together, which I don't have any, or simplify each radical and then see what they happen to be if there are any like terms. So what I mean by that is I'm going to look to rewrite 80 as a pair of factors. So I'm going to split 80 into 16 and 5. There's a lot of different factor pairs for 80, but the one that will be the most useful will be 16 and 5. I need that negative 3 still multiplied on the outside. And then I'm going to split 20. I have a 3 still on the outside. I'm going to split 20 into 4 and 5. And then I'm going to split 45 into 9 and 5. So what all I've done there is taken each radical and broken it into 2 factors where one of them is a perfect square. And now I can simplify a little further. So I have negative 3 times, and that root 16 is a 4, times root 5, plus 3 times 2 times root 5, plus 2 times 3 times root 5. So now all I've done is simplify each perfect square, which then the numbers multiply on the outside, and you should get negative 12 root 5 for the first term, 6 root 5 for the second term, and 6 root 5 for the third term. And now looking to see what adds together, I notice every single term has the same radical. They're all different, but they all simplified to be root 5, so now I can add them together. So I have negative 12 plus 6, which is negative 6 root 5, plus 6 root 5, which is actually 0. So this all adds to 0. For 21, I'm going to look to see if those add together. Right? Obviously, I have a square root of 72 and a square root of 8. They are not like radicals, so I can't add them together. So I'm going to simplify each radical first. So I'm going to try and break 72 up and 8 up into a factor pair that has a perfect square. So the factor pair I'd pick for 72 is 36 and 2, and the factor pair I'd pick for 8 is 4 and 2. Now 72, what a lot of people have a tendency to do is like square root of 8 times square root of 9, and that is 72, because 9 is a perfect square, but there's actually a larger perfect square, which is 36. We're always looking for the largest perfect square factor, because it makes your simplifying a lot easier. What I mean by that is 36 and 2 is the best pair because the square root of 36 is just 6, so that first term just becomes 6 root 2, done. And then I had that 5 on the outside. I split 8 into 4 and 2, so this becomes 5 times 2 on the outside, which is 10 root 2. So then I have 6 root 2 plus 10 root 2, which adds together, since they are the same radical, to 16 root 2. For 22, I'm going to approach it the same way. Notice I have 4 different terms, trying to subtract them, add or subtract them, and then notice all 4 radicals are different. So I'm going to simplify each radical as much as possible and then see what adds and subtracts. So I'm going to split root 12 and into root 4 and root 3. 6 root 2 doesn't simplify. Square root 2 is simplified as it gets. Root 3 doesn't simplify, but that last term I would split into 36 and 2 again. So all I did was break up the radicals that had perfect squares in them in hopes that I could maybe see what adds and subtracts together. So the first term now becomes 4 times 2 on the outside, which is 8. It'll eventually be 8. 4 times 2 times root 3 minus 6 root 2 doesn't change, minus 8 root 3 doesn't change, and then this becomes, the last term becomes 5 times 6 times root 2. So I get 8 root 3 minus 6 root 2 minus 8 root 3 minus 30 root 2 when I multiply the numbers on the outside. And then what I notice is I have 2 root 3 terms and 2 root 2 terms. So if I combine the 8 root 3 minus 8 root 3, that actually adds to 0. So I don't need to write anything, but I have negative 6 root 2 minus 30 root 2, which will then combine to negative 36 root 2, and that would be my final answer. Number 23, I'm going to try and simplify the radicals as much as possible again, and then see what does combine into what are like terms that can be combined. So I'm going to split 18 into 9 and 2. Notice that the square root of 36 is a perfect square, so that's just going to be plus 6. Minus, and then it's going to be 3 times, and then I'm going to split 50 into 25 and 2. And then negative 3 root 4, I'm going to change that root 4 to 2 since root 4 is a perfect square. And then next line, I would simplify that square root of 9, which is 3, so that first term becomes 3 root 2 plus 6. And then square root of 25 is 5, so that becomes 3 times 5 on the outside, which is 15 root 2. Minus 3 times 2 is 6. So if I look at what terms I have now, I have a positive 6 and a negative 6 add to 0, so they actually cancel out. And then I have 3 root 2 minus 15 root 2, which is negative 12 root 2. And that would be it. Number 24, similar to a problem we did before where it's a fraction. So the first thing I'm going to do is split it into 2 separate radicals. And then I'm going to look at the top, which is a perfect square, and I'm going to call that 6 over root 8. Now you can try and simplify the square root of 8 right now. What I think is the easier method to do is to actually just rationalize right now. So what I would do is multiply the top and bottom by the square root of 8, and here's what happens in the bottom. So I get 6 root 8 in the top, and root 8 times root 8 is the square root of 64, which is 8. So now all I would need to do is simplify the square root of 8, and then I'd be done. So I'm going to split the square root of 8 into 4 and 2. And then the square root of 4 is 2, so what I end up with is 12 root 2 over 8, which I would take as an answer, or if I wanted to divide 12 and 8 both by 4, I can call it 3 root 2 over 2. I would take either of those answers. It's all I will really require is that the radicals are simplified as much as possible, but if this is a multiple choice question by chance, you might have to recognize that those are you might have gotten 12 root 2 over 8, but the only possible choice maybe would have been 3 root 2 over 2. So you have to check that and be careful there. And then the last one here, number 25, first thing I'm going to do is split it into two fractions, square root of 3 over the square root of 6. And then neither of those radicals simplify at all, so I'm actually just going to multiply by the radical in the denominator to rationalize. So I end up with root 18 over 6, because root 6 times root 6 is root 36, which is 6. And then I'm going to break root 18 into the square root of 9 over times the square root of 2. And then I can call that 3 root 2 over 6. And if you want to leave that, that's fine. Or the other answer could be, if you divide the top and bottom both by 3, root 2 over 2. So both of those are acceptable for number 25. So that's all of simplifying radicals: multiplying, dividing, adding, subtracting, and just rationalizing. So if you can do all those types of problems, then you should be in great shape for the final.